what's up, my chemistry people? It is Mr. Boylan. Yeah! Today, we're going to express the arrangement of electrons in atoms through electron configurations. And if you didn't realize it was important by this video, here's your hint. Electron configurations are important. Breaking it down a little bit differently, this time we're going to look at electron configurations for the atoms of any element using what's called noble gas notation. In addition, a couple bonus features here. I'm going to slip in some important vocabulary words, especially for those of you coming back for the AP Chem course. Okay, so first, just keep in mind that a noble gas configuration is an electron configuration that utilizes a noble gas which has its valence or outermost level fully occupied by electrons. So as we take a quick peek at our tabla periodica, our noble gases are going to be over here in group 8. And as we take a look at the standard configurations for each of those noble gases, notice that they each represent a complete energy level. Boom! Helium, complete first energy level. Neon, complete second energy level. And the pattern continues. Noble gases, complete valence levels. Why do you care about this? Noble gas configurations are often used to help shorten the electron configurations of those elements that contain large numbers of electrons. As a quick example, let's take our element sodium. I'm going to jump over to this orbital periodic table, highlight my element sodium here, and write the standard configuration. Sodium's configuration, 1s2, 2s2, 2p6, 3s1. Whew, now that was kind of intense. How can we shorten that? Such a good question. What you need to do is find the noble gas that comes directly before the element that you're working with. As I look at my periodic table, the noble gas that comes directly before sodium is neon. Let me now write the electron configuration for neon. 1s2, 2s2, 2p6. Boom. Neon. What you should recognize is that this part of the electron configuration of sodium is identical to the entire configuration for neon. And so, to make your life easier, sodium's configuration can also be written by putting the symbol for neon in brackets and then picking up where neon left off. In this case, 3s1. So, these two configurations are equivalent configurations for sodium. Standard configuration, noble gas configuration. Boom! Alright, if you thought you were done, I'm going to slip in some quick vocabulary words here that are going to be really important, especially when you take the AP Chemistry course. First, isoelectronic configurations. These occur when you have two elements and or ions that have the same electron configurations as one another. Take a look at the aluminum ion and the oxide ion. Both of them have identical or isoelectronic configurations. Isoelectronic. We also have some substances that we say are paramagnetic, and those are characterized by unpaired electrons in a configuration. And due to the unpaired electrons, the atom or ion can be attracted into a magnetic field. Great example of a paramagnetic element would be iron. Bunch of unpaired electrons, paramagnetic. Then we also have diamagnetic, diagonally. Diamagnetic substances are characterized by paired electrons and there are no unpaired electrons. These atoms cannot be attracted into a magnetic field. Boom, zinc. Classic example of a diamagnetic element, all of its electrons are paired. Diamagnetic. And lastly, again for the AP class, keep in mind there's a difference when describing the electron configurations when you're adding versus removing electrons. When you're adding, you're always going to start at hydrogen and move through the periods until you arrive at the desired element. That's what we've been doing. So boom, we start here and you just go period by period until you reach whichever element you're working with. When removing electrons, however, once you get to the element scandium, the energy of the 3d orbitals actually becomes slightly less than that of the 4s. That remains true across the rest of the transition metal series. So basically it comes down to energy. And although you're filling the lowest energy orbitals first, and when filling the 4s is lower energy, once filled, the 4s actually has slightly higher energy than the 3d. So they'll be removed from the 4s first. Quick example, take a look at the configuration for iron. It has 2 valence electrons in that 4th main energy level. It's written just like all the configurations we've been discussing. But when you're describing the ions, when it has lost electrons, it's first going to lose them from that 4s sublevel. So check out the iron 2+ cation. Notice the 2 electrons that were removed to give it that 2+ charge came from the 4s sublevel. Iron will also commonly form the iron 3 ion, and at that point it will remove the electrons from the 3d sublevel. Okay, that is it. We are done for electron configurations. Again, if you're in the pre-AP class, you can enjoy those vocabulary words, but they won't be required for the test.